this code sample, several libraries are imported that will be used in the stock analysis project. NumPy is imported as NP. NumPy provides functions for numerical operations and array manipulations. Import pandas as PD. It imports the pandas library, which is used for data manipulation and analysis. By using data frames, you can easily handle and analyze data. A Python plotting library, matplotlib, includes a pyplot module and its pyplot module. Visualizations like line plots, bar plots, and scatter plots can be created. Import Seaborn as SNS. It imports the Seaborn library, which is built on top of matplotlib and provides a high-level interface for creating informative and attractive statistical graphics. The pandas_data_reader library imports the data module. We can retrieve financial data from various sources, such as Yahoo Finance, Google Finance, or AlphaVantage, using this module. Import datetime from datetime. This imports the datetime module, which provides classes for working with dates and times. Date and time will be specified for stock data retrieval. Using these libraries, the code sets up the necessary tools and functions for stock analysis and visualization. The following code snippet sets the beginning and ending dates for the stock analysis. Today equals datetime.now. This line retrieves and assigns the current date and time to the variable today. To obtain the current date and time, it uses the datetime.now function. Here, year_ago is set to a date that is 1 year earlier than today, today.year1, today.month, today.day, a year ago today, today.year1, today.month, today.day. As a result, the current year is subtracted from the today.year attribute, which represents today's date, while the month and day remain unchanged. So, essentially, this code sets the today variable to the current date and time, and the year_ago variable to a date that is exactly 1 year before the current date. Data for the analysis will be retrieved from these dates at the beginning and end of the period. The code imports stock market data for 4 different companies: Twitter, TWTR, Tesla, TSLA, Microsoft, MSFT, and Amazon, AMZN. Each company's stock market data is read from CSV files using the pandas library. Data is stored in separate variables named TWTR, TSLA, MSFT, and AMZN. There is also a list called company_list that contains the names of the 4 companies. In the code, this list can be used for data extraction or other operations involving these companies. TWTR.head5 retrieves the first 5 rows of data from the variable TWTR, which contains the stock market data for Twitter in a data frame, tabular data structure. Using the head function with the argument 5, the code returns the top 5 rows of the data frame. By doing this, you can quickly view the initial records of the dataset and see how it is structured and what the values are. In the code TSLA, head 5, the first 5 rows of data are retrieved from the variable TSLA, which represents the company Tesla's stock market data in a data frame. By using the head function with an argument of 5, the code returns the topmost 5 rows of the data frame. In this way, you can examine the structure and values of Tesla's stock market performance data pertaining to the initial entries in the dataset. It retrieves the first 5 rows from the variable MSFT, which is assumed to contain a data frame containing stock market data for Microsoft. Similarly to the previous explanations, the head function returns the top 5 rows of the data frame with an argument of 5. By doing so, you can quickly examine the initial records in the dataset, giving you insight into its structure and values. Using the code AMZN. Head 5, the first 5 rows of data are retrieved from the variable AMZN, which contains a data frame representing Amazon's stock market data. To retrieve the topmost 5 rows of the data frame, this code snippet uses the head function with an argument of 5. This allows you to quickly inspect the dataset's initial records, which provides an overview of the data structure and values pertaining to Amazon's stock market performance. Based on the assumption that TWTR is a data frame containing stock market data for the company Twitter, the code twtr.info provides information about the variable TWTR. With info, you can find out how many rows and columns the data frame has, what the columns' data types are, and how much memory it uses. It provides a summary of the dataset's data structure and provides insights into the types of data stored in the data frame, so you can better understand the overall characteristics of Twitter's stock market performance. Here is a code snippet that plots Twitter, TWTR's adjective close price data using the matplotlib library. The following steps will guide you through the process. plt.figure fig size equals 15, 7. This specifies the size of the figure, the plot. Figure size in inches is specified by the fig size parameter. Plot the adjective close price data from the TWTR data frame using plt.plot TWTR adjective close. Twitter's adjusted closing prices are visualized over time. Twitter's stock closing price on each date is represented by the points on the plot. An x-axis label will be added to the plot using plt.label_date. This indicates that the axis represents time or date. A label indicating that the y-axis represents the price of Twitter's stock is added with plt.label_price. Using plt.grid, you can visualize the data points and trends on a grid. With plt.show, you can visualize Twitter's historical price trend on the screen. This code visualizes and analyzes Twitter's historical price movements using a line plot. This code snippet creates a line plot of Tesla's DSLA adjective close price data using the pandas library. Here's how it works. This selects the adjective close column from the TSLA data frame, which represents Tesla's stock closing prices adjusted for inflation. It plots the selected adjective close data as a line graph with legend equals true and fig size equals 15, 6. Line graphs can be interpreted using a legend displayed with the legend equals true argument. The fig size equals 15, 6 argument specifies the size of the figure, the plot, with a width of 15 inches and a height of 6 inches. In summary, this code helps visualize Tesla's adjusted closing prices over time using a line plot. Tesla's stock price can be analyzed to identify patterns or trends. This code calculates the moving averages, MA, for a given set of days, 10, 20, and 30, for the adjective close price data of 4 different companies, Twitter, TWTR, Tesla, TSLA, Microsoft, MSFT, and Amazon, AMZN. Here's a step-by-step explanation. MA_days equals 10, 20, 30. This line defines a list called MA_days that contains the number of days for which moving averages will be calculated. The subsequent lines inside the for loop iterate over each value in MA_days. Ma_str equals MA, format Ma. This line creates a string with the format MA, X, where X represents the number of days for the moving average. B, TWTR Ma_str equals TWTR adjective close. Rolling Ma. Mean, this line calculates the moving average for the adjective close price data of Twitter, TWTR, over X days and stores the result in a new column named Ma_str within the TWTR data frame. C. The same process is repeated for the DSLA, MSFT, and AMZN data frames, calculating and storing the moving averages for each respective company. In summary, the code calculates the moving averages for different time periods and adds these values as new columns in the respective data frames for the 4 companies. This allows for further analysis and comparison of the moving average trends for their stock market performance. For a specified company's stock market data, the code defines a function called plot_graphic, which creates a graph illustrating the adjusted closing prices and 3 moving averages, MA, 10, MA, 20, and MA, 30. The function takes 2 parameters, company, which represents the data for the company, and company_string, which represents the company's name. Using plt.figure fig size equals 15, 6, the function specifies a width of 15 inches and a height of 6 inches for the graph. The next step is to plot 4 lines of data on the graph. A company's adjusted closing prices are plotted in the first line, plt.plot company adjective close. Each of the following 3 lines plots the company's moving averages over different time periods, plt.plot company MA, 10, plt.plot company MA, 20, and plt.plot company MA, 30. An additional element is then added to the graph by the function. The title of the graph is set to the company_string, which represents the company's name. with plt.label date and plt.label price. The x-axis is labeled as date and the y-axis is price. Using plt.legend adjective close, MA, 10, MA, 20, MA, 30, a legend is added to the graph with the labels adjective close, MA, 10, MA, 20, and MA, 30. The plot can be easily interpreted with a grid added by plt.grid. Lastly, plt.show is used to display the graph. An effective way to visualize adjusted closing prices and moving averages of a specific company's stock market data is to use the plot_graphic function. Over time, it makes it easier to analyze and compare price trends. The code snippet shows an iteration process using a list of datasets, known as data_list. Data_list consists of 4 datasets corresponding to 4 different companies: Twitter, TWTR, Tesla, TSLA, Microsoft, MSFT, and Amazon, AMZN. This iteration invokes the plot_graphic function for each dataset, passing the relevant company data and company name as arguments. Taking it step by step, here's what you need to know. A list of datasets for each of the 4 companies is created in data_list by the line data_list equals TWTR, TSLA, MSFT, AMZN. The next step involves iterating over each item in data_list by leveraging its range of length. For each I in range len data_list, we perform the following statements. For I in range len data_list. In the loop, plot_graphic is called with 2 arguments, the ith dataset from data_list and the ith company name. It is possible for the function to access relevant company data and names by using data_list I and company_list I. As a result, plot_graphic can display individual graphs for each company, displaying their adjusted closing prices and moving averages. Datasets for different companies are iterated through in the data_list. A plot_graphic function is invoked for each dataset, with the corresponding company data and name provided as input. As a result, distinct graphs are created for each company, which allow visualization of their adjusted closing prices and moving averages. This code snippet calculates the daily returns for each company within the data_list and visualizes the distribution of these returns using a histogram. A breakdown of the code can be found here. Data_list is iterated over by a for loop, which leverages the range of its length. This loop allows the code to process the data for each company individually. The data_list I daily returns is calculated by data_list I adjective close, PCT_change within the loop. This line computes the daily percentage change in stock prices by taking the percentage change in the adjective close prices for the ith company's dataset. In the dataset, a new column titled Daily Returns is created. In the following line, sns.displot data_list I daily returns. Dropna, bins equals 50, color equals blue, today equals true, uses Seaborn's displot function to generate a histogram plot. Plotting the daily return distribution for the ith company is shown here. Using the data_list I daily returns argument, the data to be plotted is provided, while removing missing values, nan, using the dropna method. The plot is also customized with 50 bins, blue-colored histogram bars, and a kernel density estimate, KDE. From the company_list, plt.title company_list I assigns the plot's title to the name of the ith company. By doing this, each plot will be labeled with the name of the company corresponding to it. Lastly, plt.show displays the current company's histogram plot. Next, the loop is iterated for the remaining companies, repeating the process for each. As a result, the provided code produces individual histogram plots of the daily returns of each company's stock prices. Analysis of the behavior and volatility of each company's stock returns can begin by analyzing the variations and patterns in the plots. Several operations are carried out using the pandas library in the provided code. First, it imports the pandas library, denoted by import pandas as PD. In this way, pandas can be used to manipulate and analyze data. The next step is to create a list called daily_returns_list by using a list comprehension. Each dictionary and data_list is iterated through to retrieve the values associated with the key daily returns. Each of these values represents the daily returns of different companies represented by pandas series objects. Stock_returns is generated by concatenating the pandas series objects from daily_returns_list along the columns axis using the pd.concat function. A combined view of the daily returns data for all of the companies is provided by this data frame, in which each column represents the daily returns of a different company. Stock_returns. Columns company _list ensures that the column names in stock_returns align with the names of the companies. Lastly, stock_returns.head is used to display the first few rows of the resulting data frame. In this way, it is possible to quickly see the structure and values of the combined data of all the company's daily returns. A list of dictionaries containing daily returns data for different companies is processed by this code. It allows comparison and analysis of the daily returns across companies by concatenating them into a single data frame. Stock_returns, the resulting data frame, consolidates the daily returns by company, with each column denoting a specific company. In this code snippet, sns.pairplot stock_returns.dropna uses the Seaborn library to create a scatter plot matrix based on the stock_returns data frame. A breakdown of the code can be found here. The sns.pairplot function produces a grid of scatter plots that display pairwise comparisons of variables within a dataset. The stock_returns data frame will be plotted with pairplot. The stock_returns.dropna operation ensures that the scatter plot matrix contains complete data. The dropna function removes any rows in stock_returns that contain missing values, denoted as nan. Seaborn's pairplot function is used to create a scatter plot matrix. In this matrix, you can see how variables within the stock_returns data frame are related pairwise. Dropna ensures that data for scatter plots is complete. The resulting plot can provide insight into the correlations and patterns between the daily returns of different companies. A heat map plot is generated to visualize the correlations between stock_returns and the correlation matrix created in the provided code snippet. The code is explained in detail below. In the stock_returns data frame, core equals stock_returns.core calculates the correlation between the columns, companies. As a result, the core variable represents a new data frame containing the correlation matrix. This line uses NumPy's trie function to create a Boolean mask using core equals np.ones_ like core, dtype equals bool. A true value is set in the upper triangle of the correlation matrix, while a false value is set in the lower triangle. As it only keeps unique correlations, this triangular mask is useful for hiding redundant and mirrored correlations. A heat map plot is prepared by setting the width and height of the plot to 10 inches with plt.figureFigSize equals 10, 10. sns.heatmap core, mask equals mask, square equals true, line widths equals .5, onNote equals true, uses Seaborn's heatmap function to create the actual heat map. Using the correlation matrix core as input, it hides redundant correlations, uses square-shaped cells in the heat map, sets the line width of the heat map cell borders to 0.5, and displays correlation values inside each cell. The final step is to display the heat map plot on the screen with plt.show. To summarize, this code calculates the correlation matrix for the stock_returns data frame and plots the correlations using a heat map. With color intensity indicating the strength of correlation, the resulting plot helps explain the relationships between daily returns of different companies. Redundancies are removed from the heat map using the triangular mask, ensuring only unique correlations are shown. With the provided code, you can create a joint plot to visualize relationships between variables in a given dataset by using the function draw_joint_plot. The code is explained in the following steps. This line introduces the draw_joint_plot function with a single parameter, data, representing the dataset to be visualized. Line grid equals sns.pairGridData.dropna, then constructs a pairGrid object based on the input data. Pairgrids allow pairwise comparisons of variables using a grid of subplots. A row in the dataset containing missing values, NINS, is removed prior to creating the pairgrid using the dropna function. Grid.map_diag_sns.histplot, bins equals 40, today equals true, associates a histogram plot to the pairgrid diagonal subplots. In this example, the histograms are generated with 40 bins using the Seaborn library's sns.histplot function. A regression plot is then mapped to the lower triangle subplots of the pairgrid using grid.map_lower sns.rigplot. sns.rigplot creates scatter plots with regression lines, illustrating the relationship between variables visually with the help of the Seaborn function. A kernel density plot is assigned to the upper triangle subplots of the pairgrid through grid.map_upper sns.ktplot. Using sns.ktplot from Seaborn, this plot visualizes kernel density estimation. Drawing a joint plot using a pairgrid from the Seaborn library is the purpose of the draw_joint_plot function. A variety of subplots are shown here, including histograms with KDE curves diagonally, scatter plots with regression lines, and kernel density plots. Combined, these visualizations illustrate how variables within a dataset are related. Here is a command for drawing a joint plot using stock_returns data. A joint plot combines two plot types, scatter plots and histograms. This method is commonly used to analyze the relationship between two variables and their individual distributions. To create this joint plot, the code probably uses a data visualization library, such as Seaborn in Python or Matplotlib in R. This plot is generated using a dataset containing stock return information. This code will create a joint plot displaying the relationship between two variables in the stock_returns dataset. The scatter plot in the center shows the correlation between these two variables, while the histograms on the top and right show the distributions of each variable separately. Using this visualization, users can identify patterns, trends, and potential outliers in the data. This code calculates the mean income and covariance of stock returns for a given dataset of stock returns. It then prints the mean income and covariance matrix. Here's a step-by-step explanation. Mean_income equals stock_returns.mean. This line calculates the mean income for each stock in the dataset. The mean function computes the average value of each stock's returns. Covreturns equals stock_returns.cov. This line calculates the covariance matrix of the stock returns. The cov function computes the covariance between each pair of stocks in the dataset. Covariance is a measure of how two variables change together, and it is used to assess the risk and diversification potential of a portfolio. Count equals len stock_returns.columns. This line calculates the number of stocks in the dataset by counting the number of columns in the stock_returns data frame. Print mean_income, cov_returns, sep equals in. This line prints the mean income and covariance matrix, separated by a new line character. The sep equals / an argument specifies that the two outputs should be printed on separate lines. In summary, this code calculates and prints the mean income and covariance matrix for a dataset of stock returns, which can be useful for analyzing the performance and risk of a portfolio. The provided code defines a function called random portfolio that is responsible for generating a random portfolio of shares. Here's a breakdown of what the code does. Def random portfolio, this line introduces the random portfolio function. Share equals np.expnp.random.random count. This line uses NumPy's random number generator to generate an array of random numbers from a standard normal distribution. The size of the array is determined by the count variable. The np.random.random function generates random numbers with a mean of 0 and a standard deviation of 1. The np.exp function is then applied to each random number, resulting in a set of positive values. This step ensures that the generated share values are non-negative. Share equals share.sum. This line normalizes the generated share values by dividing each value by the sum of all the share values. This normalization step ensures that the sum of all shares in the portfolio adds up to 1, representing a proportion of the total portfolio value. This way, the generated share values reflect the weight or allocation of each share in the portfolio. Return share. This line returns the generated share values as the output of the function. In summary, the random portfolio function generates a random portfolio of shares by drawing random values from a standard normal distribution, exponentiating them to ensure positive values, and then normalizing them to represent proportions of the total portfolio value. By calling this function, you can obtain a random allocation of shares for a portfolio. The provided code includes two functions, income portfolio rand and risk portfolio rand. These functions are designed to perform calculations related to income and risk for a portfolio. The income portfolio rand function takes one parameter, rand. It calculates the expected income of a portfolio by performing a matrix multiplication between mean_income.values and rand. The mean_income.values variable represents the mean income values associated with different assets or investments, while rand represents the allocation or weights assigned to each asset in the portfolio. The result of the matrix multiplication is the expected income for the portfolio. The function then returns this expected income value. The risk portfolio rand function also takes one parameter, rand. It calculates the risk of a portfolio using a series of matrix multiplications. The cov_returns.values variable represents the covariance matrix of the returns of different assets, while rand represents the allocation or weights assigned to each asset in the portfolio. The innermost matrix multiplication, np.metmul rand, cov_returns.values, calculates the weighted covariance of the portfolio. The outer matrix multiplication, np.metmul rand, cov_returns.values, ran, further calculates the risk of the portfolio. The square root of this value, obtained using np.sqrt, represents the standard deviation of the portfolio's returns and indicates the level of risk. The function then returns this risk value. In summary, The income portfolio REN function calculates the expected income of a portfolio based on the mean income values and the allocation of assets. The risk portfolio REN function, on the other hand, calculates the risk of a portfolio based on the covariance matrix of returns and the allocation of assets. Together, these functions provide essential metrics for evaluating the income and risk characteristics of a portfolio. The provided code snippet appears to be a part of a portfolio optimization process. Let's go through the code step by step to understand its functionality. First, the variable combinations is initialized to 4000. This variable determines the number of portfolio combinations that will be generated and evaluated. Next, 3 arrays named risk, income, and portfolio are created and initialized with zeros. These arrays will store the risk, income, and portfolio data for each combination. A for loop is used to iterate over each combination. The loop runs from 0 to combinations, 1, generating a total of combinations portfolios. Within the loop, the function random portfolio is called to generate a random portfolio. The exact implementation of this function is not provided in the given code snippet, but it likely generates a set of shares along with their corresponding weights. The randomly generated portfolio is then assigned to the nth row of the portfolio array. Each row in the portfolio array represents a different combination of shares. Next, the risk portfolio function is invoked, passing the current portfolio as an argument. This function calculates the risk associated with a given portfolio. Unfortunately, the code does not provide the specific implementation of this function. The calculated risk value is assigned to the nth element of the risk array. Following that, the income portfolio function is called with the current portfolio as an argument. This function computes the income or expected return of the portfolio. Similarly, the code snippet does not provide the details of this function's implementation. The calculated income value is then assigned to the nth element of the income array. After the completion of the loop, the risk, income, and portfolio arrays will contain data for each generated combination of shares. The portfolio array will have dimensions, combinations, count, where count represents the number of shares in each portfolio. The risk and income arrays will have a length of combinations, corresponding to the risk and income values for each combination of shares, respectively. The provided code snippet utilizes the matplotlib library to create a scatter plot visualizing the relationship between risk and income, which were calculated in the previous code. Let's break down each line to understand its purpose. plt.figure fig size equals 15, 8. This line creates a new figure with dimensions of 15 inches by 8 inches, defining the size of the plot. plt.scatter risk 100, income 100, c equals b, marker equals. This line generates a scatter plot using the risk and income data. The risk values, multiplied by 100, are plotted on the x-axis, while the income values, also multiplied by 100, are plotted on the y-axis. The scatter plot points are represented by blue dots with a dot marker style. plt dots label risk. This line sets the x-axis label as risk, providing a descriptive label for the risk axis. plt dot label income. This line sets the y-axis label as income, providing a descriptive label for the income axis. plt.title portfolios. This line sets the title of the plot as portfolios, providing a descriptive title for the scatter plot. Max Sharpe ratio equals np.argmax income, risk. This line calculates the index of the portfolio with the maximum Sharpe ratio by dividing the income values by the risk values and finding the index with the highest ratio. plt.scatter risk max Sharpe ratio, 100, income max Sharpe ratio, 100, c equals r, marker equals o. Label equals max Sharpe ratio. This line plots a single red dot at the risk and income values of the portfolio with the maximum Sharpe ratio. The dot is colored red, R, and has a circle marker style, O. A label max Sharpe ratio is added for this point in the legend. plt.legend. This line displays the legend on the plot, which includes the label for the portfolio with the maximum Sharpe ratio. plt.show. This line shows the plot, displaying it on the screen. In summary, the code snippet generates a scatter plot where the x-axis represents the risk and the y-axis represents the income for multiple portfolios. It further highlights the portfolio with the maximum Sharpe ratio by adding a red dot at its corresponding risk and income values and including a legend to identify it. The scatter plot provides a visual representation of the risk and income relationship for the portfolios. This code snippet retrieves the portfolio with the maximum Sharpe ratio, which is stored in the variable best_port. Then, it loops through each element of the company_list and prints the company name along with the corresponding allocation or weight of that company and the best portfolio. In simpler terms, the code identifies the portfolio with the highest Sharpe ratio and then displays the allocation or weight assigned to each company in that portfolio. It allows us to see how the assets or companies are distributed within the best performing portfolio. Try to predict price behavior with method Monte Carlo. This code snippet calculates the average daily returns, mu, and the standard deviation of daily returns, sigma, for a stock. Here's what each line does. Days equals 365. This line assigns the value 365 to the variable days, representing the number of days in a year. It assumes that the stock data represents daily returns over a year. dt equals 1 days. This line calculates the time interval, dt, between each data point by dividing 1 by the number of days in a year. It determines the fraction of a year between each data point. Stock_returns.dropNA in place equals true. This line removes any rows with missing values, nan, from the stock_returns dataset. The in place equals true parameter ensures that the changes are applied directly to the dataset. Mu equals stock_returns.mean. This line calculates the average, mean, daily returns for the stock. It computes the mean value across all the data points in the stock_returns dataset. Sigma equals stock_returns.std. This line calculates the standard deviation of the daily returns for the stock. It measures the variability or volatility of the stock's performance by computing the standard deviation of the data points in the stock_returns dataset. In summary, the code calculates the average daily returns, mu, and the standard deviation of daily returns, sigma, for a stock based on the available data. These values are commonly used in financial analysis and risk assessment to understand the historical performance and volatility of a stock. The provided code snippet introduces a function named Monte_Carlo that employs the Monte Carlo method to simulate the future price of a stock. Let's examine the purpose of each line. The function Monte_Carlo is defined, taking 4 parameters: start_price, initial stock price, days, number of simulation days, mu, average daily return of the stock, and sigma, standard deviation of the stock's daily returns. The price array is initialized with zeros to store the simulated stock prices for each day of the simulation. The initial price is assigned to the first element of the price array. 2 arrays, shock and drift, are initialized with zeros. These arrays will hold the random shocks and drift components for each day of the simulation. A loop is initiated to iterate over the days of the simulation, starting from the second day. Within the loop, a random shock for the current day is generated using a normal distribution based on the provided average daily return, mu, the time interval, dt, and the standard deviation of daily returns, sigma. The drift component for the current day is calculated, representing the expected change in price based on the average daily return, mu, and the time interval, dt. The simulated price for the current day is computed by applying the drift and shock components to the previous day's price. The result is stored in the price array. Once the loop completes, the function returns the price array containing the simulated prices for each day of the Monte Carlo simulation. In summary, the Monte_Carlo function uses the Monte Carlo method to generate simulated stock prices for a specified number of days. It considers the initial stock price, average daily return, and standard deviation of daily returns. The function incorporates random shocks and drift components to calculate the simulated prices for each day. Finally, it returns an array containing the simulated prices. The code snippet in question carries out a Monte Carlo analysis for Twitter stock, which is denoted by the ticker symbol TWTR. It commences by assigning the initial stock price of Twitter at $35.65, as indicated by the line start_price equals 35.65. The next line, sim equals np.zeros 1000, establishes an array named sim composed of 1000 zeros. These zeros are placeholders for the final predicted stock prices following the Monte Carlo simulations. For the forthcoming plot, a new figure is generated with dimensions 15 inches by 8 inches, as suggested by plt.figure fig size equals 15, 8. The line for I in range 1000 initiates a loop that runs 1000 times, each iteration representing a Monte Carlo simulation. The Monte_Carlo function is then called upon with the initial price, number of days, and Twitter's specific average daily return, mu, and standard deviation of daily returns, sigma. This is evident from the line result equals Monte_Carlo start_price, days, mu TWTR, sigma TWTR. The final predicted price from each simulation is stored in the sim array, as depicted by sim I, equals result days, 1. Each simulated price path is subsequently plotted using plt.plot result. The plot is then appropriately labeled with days on the x-axis, price on the y-axis, and Monte Carlo analysis for Twitter as the title. The lines plt. Label days, plt. Label price, plt. Title Monte Carlo analysis for Twitter perform these labeling tasks. To sum up, this code performs a Monte Carlo analysis of Twitter's stock by predicting its future prices through 1000 simulations. The final prices from these simulations are stored in the sim array and plotted. By doing so, the code offers potential insights into the future price range of Twitter's stock, as determined by the Monte Carlo simulations. The provided code snippet offers a visual representation of the Monte Carlo simulations results concerning Twitter's stock. It initiates by creating a new plot figure with dimensions of 10 inches by 7 inches, as defined by the line plt.figure fig size equals 10, 7. Then, using plt.histSim, bins equals 100, it generates a histogram of the prices simulated and stored in the sim array, dividing the data into 100 bins and plotting the frequency of prices within each bin. An important part of the visualization is the text annotation, achieved by plt.figtext 0.6, 0.7, mean, \nstd, \n start price, format sim.mean, sim.std, start price. This line places text within the figure at a specified location, displaying the mean, standard deviation, and starting price of the simulated prices. The values for these are obtained from sim.mean, sim.std, and start price, respectively. Finally, plt.show makes the plot visible on the screen. In essence, the provided code constructs a histogram to illustrate the distribution of the Twitter stock simulated prices derived from the Monte Carlo simulations. The visualization includes text annotations that outline the mean, standard deviation, and initial price of the simulated prices. This visual representation provides valuable insights into the potential range and traits of Twitter's future stock prices, as per the Monte Carlo simulations. The given code snippet executes a Monte Carlo analysis for Tesla's stock, identified by the ticker symbol TSLA. It begins by assigning the initial price of Tesla's stock at $907.34, as outlined by the line start_price equals 907.34. Subsequently, an array named sim, filled with 1000 zeros, is initialized via sim equals np.zeros 1000. This array is designed to hold the simulated final prices of Tesla's stock following the Monte Carlo simulations. A new figure, sized 15 inches by 8 inches, is then created for plotting as indicated by plt.figure fig size equals 15, 8. The line for I in range 1000 triggers a loop that will run 1000 times, each iteration representing a single Monte Carlo simulation. The Monte_Carlo function is invoked to simulate future prices of Tesla's stock, as shown by the line result equals Monte_Carlo start_price, days, mu TSLA, sigma TSLA. This function is passed the initial stock price, the number of days for the simulation, and Tesla-specific average daily return and standard deviation of daily returns. Each simulation's final price is stored in the sim array, as denoted by sim I, equals result days, 1. The simulated prices for Tesla's stock from each Monte Carlo simulation are then plotted using plt.plot result. The plot's x-axis and y-axis are labeled days and price, respectively, and the plot's title is set as Monte Carlo analysis for Tesla, as depicted by plt.label days, plt.label price, plt.title Monte Carlo analysis for Tesla. In conclusion, this code snippet conducts a Monte Carlo analysis for Tesla's stock by predicting its future prices through 1000 simulations. The final prices are stored in the sim array and subsequently plotted. The axis and plot title are appropriately labeled. This analysis aims to provide potential insights into the future price range of Tesla's stock, as predicted by the Monte Carlo simulations. This code generates a histogram plot to visualize the distribution of simulated prices for the Tesla stock obtained from the Monte Carlo simulations. Here's a breakdown of each line. plt.figure fig size equals 10, 7. This line creates a new figure for the plot with dimensions 10 inches by 7 inches. plt.histSim, bins equals 100. This line generates a histogram plot using the data from the sim array. The sim array contains the simulated final prices of the Tesla stock from the Monte Carlo simulations. The histogram divides the data into 100 bins, representing the frequency or count of prices within each bin. plt.figtext 0.6, 0.7, mean, \nstd, \n start price, format sim.mean, sim.std, start_price. This line adds text annotations to the figure at specific coordinates. It displays the mean, standard deviation, and start price of the simulated prices using the sim.mean, sim.std, and start_price values, respectively. The format method is used to format the text string with the calculated values. plt.show, this line displays the plot on the screen. In summary, the code generates a histogram plot to visualize the distribution of simulated prices for the Tesla stock obtained from the Monte Carlo simulations. The plot helps understand the potential range and characteristics of the simulated prices. The text annotations provide additional information such as the mean, standard deviation, and start price. This visualization aids in analyzing the results of the Monte Carlo analysis for the Tesla stock. To provide the tail, last few rows, of the Microsoft MSFT dataset, I would require access to the specific dataset or a direct link to it. As an AI language model, I don't have real-time access to live data or specific datasets unless provided by the user. However, you can typically obtain the tail of a dataset in Python using the tail method. The provided code snippet performs a Monte Carlo analysis for the stock of Microsoft, represented by the ticker symbol MSFT. Here's a breakdown of each line. Start_price equals 300.95, this line sets the initial price of the Microsoft stock to $300.95. Sim equals np.zeros 1000, this line initializes an array called sim with 1000 zeros. The purpose of this array is to store the simulated final prices of the Microsoft stock after conducting the Monte Carlo simulations. plt.figure fig size equals 15.8. This line creates a new figure for plotting, specifying its size as 15 inches by 8 inches. For I in range 1000, this line initiates a loop that will iterate 1000 times, representing the number of Monte Carlo simulations to be performed. Result equals Monte_Carlo start_price, days, mu MSFT, sigma MSFT. This line calls the Monte_Carlo function to simulate the future prices of the Microsoft stock. It passes the initial stock price, the number of days to simulate, and the average daily return and standard deviation of daily returns specific to the Microsoft stock. Simi equals result days, 1. This line stores the final price of the Microsoft stock obtained from the Monte Carlo simulation in the sim array. It saves the price at the last day of the simulation. plt.plot result, this line plots the simulated prices for the Microsoft stock obtained from the Monte Carlo simulation. plt.label days, plt.label price, plt.title Monte Carlo analysis for Microsoft. These lines set the x-axis label as days, the y-axis label as price, and the title of the plot is Monte Carlo analysis for Microsoft, respectively. In summary, the code snippet performs a Monte Carlo analysis for the Microsoft stock by simulating its future prices. It runs 1000 simulations, storing the final prices in the sim array. The code then plots the simulated prices and labels the axes and the plot title accordingly. This analysis provides insights into the potential range of future prices for the Microsoft stock based on the Monte Carlo simulations. The code generates a histogram plot to visualize the distribution of simulated prices for the Microsoft stock obtained from the Monte Carlo simulations. The plot helps understand the potential range and characteristics of the simulated prices. The text annotations provide additional information such as the mean, standard deviation, and start price. This visualization aids in analyzing the results of the Monte Carlo analysis for the Microsoft stock. To provide the tail, last few rows, of the Amazon AMZN dataset, I would require access to the specific dataset or a direct link to it. As an AI language model, I don't have real-time access to live data or specific datasets unless provided by the user. However, you can typically obtain the tail of a dataset in Python using the tail method. The code snippet performs a Monte Carlo analysis for the Amazon stock by simulating its future prices. It runs 1000 simulations, storing the final prices in the sim array. The code then plots the simulated prices and labels the axes and the plot title accordingly. This analysis provides insights into the potential range of future prices for the Amazon stock based on the Monte Carlo simulations. The code snippet generates a histogram plot to visualize the distribution of simulated prices for the Amazon stock obtained from the Monte Carlo simulations. The plot helps analyze the range and characteristics of the simulated prices. The text annotations provide additional information such as the mean, standard deviation, and start price. This visualization aids in understanding the results of the Monte Carlo analysis for the Amazon stock.